corn is one of the most important crops in the world. It can be used as medicine, food, fuel, and feed. Therefore, how to ensure the yield of corn has become one of the problems to be solved urgently. There are three main states and early stage of corn growth: healthy, stressed, and non-germinated. The situation for corn seedlings like sowing depth, planting density, and soil condition influence the health of seedlings. Unfavorable environment can cause the seedling change color. The leaves begin to turn yellow. In this situation, if no measures are taken, the leaves will die and fall off, leaving only a bare stem, which affects the normal growth of corn. Therefore, it is necessary to identify the stressed seedlings in time. The number of non-germinations is a direct factor that affects yield, and seedlings need to be refilled in time to solve the problem. So our robot's goal is to detect three germination status, see the non-germinations, present the distribution and density of corn on the visual screen, and finally send data to the server. In response to the occurrence of non-germinations, we have designed a mechanism to simplify the task. Since the release of the rules in November 2019, we have been improving and optimizing the mechanism, and there have been three versions of our concept so far. We have used the design of crawler wheels, which can greatly reduce the damage to the soil. The control of the linkage mechanism is relatively simple, which can be directly driven by the servo, but the position of seating is not precise enough. In order to improve the accuracy of seat positioning, we have designed a guide rail chute mechanism that can be positioned in 2 vertical degrees of freedom to enable precise positioning. Taking into account the excessive pressure on the ground and the possible inefficiency of the recognition system that requires real-time feedback, we decided to design the third version of the mechanism, which is also our final one, with an adaptive gear and rack seating mechanism. The precise seating tray can plan single seat through the cooperation of stepping motor and filter, and it is convenient to add seats at any time. The sewing components driven by the gear and rack can expand the seating area and meet the demand of the users. The three stages are distinguished by visual recognition system. The task is divided into 2 steps. The first is to identify the status of the plant. There are 3 cases of germination status of the standard group: healthy, stressed, and non-germination. We noticed that color is the best feature to distinguish these 3 status, so our machine vision system mainly developed color recognition methods. In order to solve the problem of random placement, we adjusted the region of interest to the lower part of the seedling. We used a lab color space to represent the image and set a appropriate threshold for 3 channels. However, the disadvantage of this method is that it is not robust enough and is easily affected by ambient light. In order to solve this problem, we designed a light system to maintain the stability of the light intensity by external LEDs. The second step is the positioning of the plant. When the recognized status is non-germination, we use image algorithm to calculate the coordinates of the center pixel and then map the coordinates to position information. The information was then passed to Arduino, which controls operation of the robot like sewing. In order to make the robot have functions such as walking, identification, seating, display, and wireless transmission, we chose Arduino as the main control board and used stepping motors, OpenMV, servos, LCD, ESP8266 to support these functions. When the robot works on the field, OpenMV will detect every position and transfer the result to Arduino, which controls the hardware to perform corresponding operations on different status and sends information to the server through ESP8266 after the operation is completed. In particular, in our formal design, we plan to transmit the data of OpenMV to Arduino through serial communication. However, during the testing process, we found that the serial communication is not accurate, and also it takes up a lot of resources of Arduino, which makes robot's working function appear to be stuck. Therefore, we gave up serial communication and used electric level. We changed the output level of 2 digital pins of OpenMV to present different germination status, and drew the map as shown in the right side figure. This method effectively avoids transmission errors and solves the stuck problem, and this is the video of our robot. First of all, we check the size of the robot, and we can see the robot can be placed in a cube with a side length of 12 inches.
3, 2, 1, go.
We chose 4 camera positions to show the robot's working process. As you can see, the main screen shows the overall working road of the robot. The lower left corner is a close-up of the LCD. It shows the robots can feedback plant information on the LCD screen in real time. An upper left corner is the GUI that can randomly arrange the status corn plants and automatically calculate time and score. The upper right corner is the tracking angle, which mainly records the showing movement of the robot. When working, the robot moves along the black tracking line. When a non-termination state is recognized, the gear and the rack drive the seating components extend outward. The adaptive mechanism is quickly adjusted to the simulated seating position. The stepping motor drives the filter to rotate so that the single seat drops down to the container. Due to the mistakes in recording video and in accordance with the principle of fair play, we place additional timer below the video to correct the error. The scores obtained by the robot, as well as the status distribution table and population density, are shown in the figure.
Okay, stop.
The total price of our robot is $157.13. Our instructor is Mr. Ye, who majors in agriculture, electrification, and automation. He gave us help and guidance when we encounter difficulties. Team member Jichun Wang is responsible for the main program code and subsequent debugging. Team member Mengyuan Chen accomplished the integration of the CSys and participated in the debugging of the real car. Team member Jintao Feng finished the design of the major mechanism and the construction of the real vehicles. Team member Zeyu took part in the debugging of our robot. Captain Youchao Zhang realized the vision system and auxiliary mechanism design. Other members are junior students who major in agricultural engineering. Finally, we want to thank the ASABE organization for providing us with this precious opportunity. In such a severe situation, you can still overcome many difficulties and ensure the normal holding of the competition, which enables us to cooperate and solve problems together. Every member in our team has gained an unforgettable experience. Let us work together to promote the development of agriculture.